So I think we can start. So hello everybody, this is Luboš Pirkl from CFD Support. Welcome to the webinar on turbomachinery design and analysis. In today's webinar, we would like to show you an easy way how to design a centrifugal fan from scratch in CFturbo, and then how to simulate and evaluate it in TCFD. The webinar is being recorded, and its recording will be made available on our YouTube channel. And yeah, I hope everything works well. So in case of any technical problems, feel free to contact us, and we will gladly answer all your questions and comments. Please let me introduce the speakers of today's webinar. So this is me. My name is Luboš Pirkl. I'm co-founder of CFD Support, and I'm gonna guide you through the webinar. And I am here in our Prague office with my colleague Radek Máca. Hello, Radek.
Hello, Luboš, and hello, everyone.
So, Radek, are you ready for the webinar?
Yes, I am ready. I'm really looking forward to my part.
Okay, thank you. So I only know that Radek is our head engineer and senior developer here at CFD Support. And yeah, he's our golden boy, and he can do miracles with computer, right? So we're glad to have him. Anyway, and together with us on the other line, there is Oliver Felde in Dresden from CFturbo. Hello, Oliver.
Hello, Luboš, and hello, Radek, and hello, everybody out there.
Yeah, hello. Great to have you here. The same question. Are you ready for the webinar?
I am ready, and I'm happy to have the opportunity to show CFturbo within that webinar today.
Okay, that's perfect. So I only note that Oliver is responsible for consultancy and CFD development at CFturbo, and especially for the implementation of turbomachinery design theory and related algorithms in CFturbo software. So this is us. About the webinar program, the webinar is going to take about 1 hour, depending on the number of your questions and also how fast we are gonna make our job. There will be 4 parts in the webinar. In the first part, there is this general introduction. In the second part, let's call it the design part or CFturbo part, there will be a live example where Oliver is going to introduce CFturbo a little bit, and then he will show a live example of centrifugal fan, its design from scratch in CFturbo software, and with the final export of the designed model to turbomachinery CFD. In the next part of this webinar, let's call it the simulation part or TCFD part, there will be other live example where Radek is going to show turbomachinery CFD simulation, and it will be simulation of that centrifugal fan exported by Oliver from CFturbo in the previous section. Yeah, and in the last part there will be a Q&A session dedicated to your questions and our answers. So feel free to put your questions to the special window. All the questions will be answered. Some of them will be answered directly in this webinar, and the rest will be answered via email. So all the answers will be answered. So feel free to put your questions. It's your time. Just take this opportunity. We are here for you, and we are ready. We are ready to support you. So this is the introduction, and now here comes the design part. So let's go on with the design part of the webinar. So I'm gonna hand over the presentation to Oliver. So Oliver, are you ready to
I am ready.
Tell us about CFturbo? Okay.
Yes, I am.
So
okay.
Switch. Yeah, go please. Yeah.
Just a couple of words about CFturbo. CFturbo is a software, a very special CAD software, which we call a conceptual design software. It's powerful, user-friendly, and so on. It uses the latest design theory on turbomachinery. Right now we have something like 200 active clients globally, and available are the following modules. Modules to design pumps, both axial and centrifugal ones, to design fans and blowers, again axial and centrifugal ones, compressors, special kinds of turbines, and of course what is necessary for those kind of designs. Also stators, vaned and vaneless plus diffusers can be designed, as well as volutes, especially if one wants to design centrifugal pumps or something like that. We serve with that software the following industries, and amongst them are aerospace, automotive, consumer products, semiconductor, and a lot more.
Okay, so now the screen is yours, Oliver.
Okay. I hope you can see my
Yes, it's perfect
now.
Yes.
Okay, thank you. What you see here is the GUI, if you like, of CFturbo. If you start something very new, the first thing you have to decide is which kind of machine you want to design. And today, because I want to do a fan live demo, I'm starting with the ventilator module. And a design from scratch always starts with the definition of the design point. Since we do a best point design, it's necessary to know what is the operating point in which the fan, for instance, will run most of the time, because if that machine is run in that operating point, then you will expect to have the fan with the best efficiency in that operating point. So for the example today, the design point is 38,000 cubic meter per hour for the flow rate, something like 0.264 bar for the total pressure difference, and the fan should run on 2,800 RPMs. And there should be air conveyed at a temperature of something like 45 centigrade. The inlet pressure is defined with 1 bar, but for the design part, this is not really necessary. It's a value that is later on used for the export of the boundary conditions for the CFD simulation. Once all these numbers are filled into the edit boxes, one gets a first set of information, and the very important number, what you can see on the right hand side, is the specific speed. And for that design point, we get something like 28, and it tells you that the best meridional contour would be those of a radial fan, and that's why this is given here also in that picture. If I press OK, the next thing I am prompted to do is to add a new component. Components can be either stators, vaneless or with blades, or volutes, or just impeller. And because the impeller is the central component of my stage, I'm going to start with that. And that's why I choose radial or mixed flow impeller. And the first design step is to define the main dimensions of the impeller, and those main dimensions are inlet diameter and the impeller diameter itself, plus the impeller at the outlet. Type in directly any dimensions that an engineer might have in mind. We can also use the built-in proposals that clicking on calculate on the calculate button. So there's not a lot of change here, because initially, if you go for the first time into such a design step, it's virtually pressed, this button here. There's also an automatic mode which you can activate, and if that is activated, then every change of a design parameter will change to, or will yield a new calculation of that main dimensions, and you will get an immediate feedback, for instance here in that preview of the meridional contour. Okay, once you are happy, you should uncheck this checkbox, and you might be you might want to get rid of decimal places, and that's what I do now here as well. So I have a suction diameter of 425. That inlet width is not necessary really, so that's also fine, and an outlet width of something like 78 millimeters. Once I press OK, I get some preview in the meridional view of CFturbo, which is not yet shaped at hub and shroud, but the inlet and outlet dimensions are set. The shape of hub and shroud will be defined in the second design step, which is the meridional contour design step. And in that design step, one gets also a preview of the 3D geometry. Initially, for that type of centrifugal fan, I get a straight or meridional hub contour, but of course I can change it at any time just by using the context menu items. So here I change it to Bezier, and now I have a couple of Bezier control points in order to define a nice contour for the hub, for instance. And very often for centrifugal fans, impeller as well as the volute are made of sheets of metal, and that's why I leave the the shroud contour to a linear part and a circular arc part. So the only one I'm going to change here is the actual extent, which can be 200, for instance. And I want to have here another linear piece at the suction mouth, and that's why I'm going to add another inlet curve, put it on my DS diameter, and also put this value to 0, and maybe adjust this circular arc diameter a bit. What I can do also is adjust that leading edge position, and also I could change the shape of the leading edge. But since I want to use again metal sheets for the blades as well, I'm going to leave it to straight. Yeah. Okay, I can check the contour or the quality of the contour by applying some potential flow simulation for the meridional velocity component here, and here I can check whether I have too much acceleration at the shroud due to the high curvature, for instance, and also I have other means to check the design at every time. So I could, for instance, check the area progression, and I could try to change the control points of the Bezier curve in order to get a desired cross-section distribution, for instance. Once I'm happy with that, I press OK. Then this meridional preview looks a bit different to the initial one, and I get also something in our 3D viewer. And what you see here is the 3D model of hub and shroud. Next design step is the definition of the blade properties. Here one can set up the number of blades. Again, one gets proposals by CFturbo. So for instance, for that radial fan, there is just a standard number of 7, which is given for a specific speed scope. But because this can be customized at any time, one can add own functions which then take into account own experiments, and those functions will be saved in a certain file and will stay with the customer. Okay, so I have 10 number of blades. I'm going to have circular 2D shape because, as I said, it should be made of metal sheets. I need to know a bit about the thickness of that metal sheet, and that has to be input into that table here. Also, I need to know a bit about the slip. I can choose either from built-in slip models, or I just, as I want to do it now, can type in a slip that I would expect for that kind of machine. At the second top, there is the blade angles, which again can be calculated by CFturbo or can be typed in by the customer itself. If they are calculated, then the Euler equation of turbomachinery will be used, plus the slip information and the incidence information. And with the help of these information, those proposals will be made, and one can accept that or can override it just as needed. Again, on the right-hand side, there are a couple of informational values. So, for instance, on the basis of that blade angles, one can calculate the complete velocity triangles at leading and trailing edge. And one see, of course, a deviation angle of 10 because that was directly defined here. But if one uses another slip model, then one would get this value of deviation angle here. Once I'm happy, I can again press OK. In the 3D model, there's no change because just blade angles at leading and trailing edge were defined. In order to get a change of the 3D geometry, the next step has to be performed. And that step is called the mean line design step, where the blade is defined with a 0 thickness if you want. And and one can see that here in the 3D preview. The left part of the window is a rather static part because we have chosen a circular 2D axial blade shape, and with this restriction, there is no chance to change anything anymore after leading and trailing edge radius are defined plus the blade angles are defined. So that's why I can go to the next step. The next step is to put some thickness onto that mean surface. Again, there are a couple of ways to do that. So for instance, I can switch it to Bezier again and can manipulate the Bezier points. I can have the leading and trailing edge rounded. But what I want to do here is I want just to stick to the simplest one, which is the linear mode, and there are a couple of control points, and between the control points the thickness is linearly interpolated. Okay, and the very last design step is to shape leading and trailing edges in 3D. So for the leading edge, I'm going to apply an elliptic shape with a axis ratio of 3. if I had an access ratio of 1, it would be circular, but I'm going to stick to 3. Whereas at the trailing edge, it's just a simple straight trailing edge, which is trimmed with the diameter of the impeller. And if I now go and see what I get in 3D, then I have this impeller ready. Because I want to run, or we want to run a CFD afterwards, there is another design step which is worthwhile to do, and the design step which is called CFD setup, allows to add a certain offset at the trailing edge, and that is good for the meshing and also for the setup of the CFD simulation. So that's why I'm going to add this too. The next step is to add a volute. Again, it's similar to the impeller design. The first design step is to tell what is the inlet definition. Here I change the inlet width of the volute to 300 and set the inlet diameter to something like 1300, for instance. And also I want to have a certain offset in Z direction, because otherwise I would have two counter-rotating secondary flow structures in the volute, and that's what I want to suppress by such an offset. Next design step is to tell what is the general shape of the cross-section of the volute, and it should be rectangular because, as I said, the volute should be made from metal sheets. So there's nothing else to be done here. The next step is to tell how is the growth of the cross-section area with the wrap angle. And one can again use some recommendations, this time on the basis of either Fleider's rule or Stepanov's rule. I'm going to stay with Fleiderer, and I get something like that. Again, there are a couple of informational values that can be used to check the design. So very often used is, for instance, the A to R ratio, which is linear for the Fleiderer rule, and this is something what is from a theoretical point of view a very good choice. Okay, almost finally, the definition of the outlet diffuser of the volute. So here I want to have it with a dimension of 400 times 300 and a certain length of 1 meter. And once I've finished that, the very last design step is just to define the cutwater, and the first parameter is to set where should it start. So it should start at a wrap angle of 30 degrees. I can also change the cutwater height, and here you see in the preview how it would look like. And if I now press OK and go to the 3D model, then everything is defined, and I can start to export the geometric data into any format that is used by the simulation package. But before I do that, I'll run again a CFD setup for the volute, and it's given here. And as I know that there are some rules for the names of the components, if I want to use the TCFD interface, I'm going to change the names of my components and get rid of some characters here, and that's why I just go for impeller 1 and volute 1, and now I'm going to save that in a certain directory and call it fan. And the very last step is to run what we call the model finishing, and in the model finishing, all the surfaces that have been defined so far will be extracted a bit, and then the intersections of those surfaces will be calculated, and using some 3D Boolean operations, a very clean 3D geometry of the fluid negative will be generated. At this time, one can also introduce some fillet at hop and shroud, but I'm not going to do that here for the time being, or for the sake of time. And after a couple of seconds, I'm ready with that, and now I'm able to export my geometry into various formats, and already checked is the TCFD format. The last thing I have to do is to select which of the components I want to export. Of course, I'm going to have all the components, and also I can tell him where to export the things to, and also I can set some parameters, because apart from the control file, which holds all the information necessary to set up the CFD run in TCFD, also STL data are exported, and one can adjust the coarseness, for instance, or the size of minimum or maximum elements in that panel here. But again, I leave it to default, start the export, and by doing so, I am ready and I can pass over the presentation control to Radek. Last word probably, now you see all the STL data have been exported successfully, plus a control file with the ending TCFD, and this control file holds all the necessary simulation information.
Okay, thank you, Oliver, for the design part. So now the centrifugal fan was designed, and now it's time to go on with the simulation part of the webinar. So I will switch the presentation back to me. Yes, and I will give a brief description what is turbomachinery CFD. So turbomachinery CFD is a unique software developed in Czech company CFD Support. It's smart, easy to use, and affordable CFD software. Turbomachinery CFD was designed for CFD simulations of all rotating machinery, such as fans, pumps, compressors, turbines, turbochargers, hydro turbines, both radial and axial machines, both compressible and incompressible fluid flows. It's based on OpenFOAM, and we believe turbomachinery CFD is unique, at least for 4 reasons. So number one would be we use no licensing policy, which means turbomachinery CFD is perpetual and can be used by our users in an unlimited way. So it can be used by unlimited number of users, jobs, or cores, and for this reason it can scale a lot the potential of CFD simulations. TCFD is fully automated, so all the workflow can be run by a single click or a single command, which makes it extremely effective. Also, we have very good technical support, so we are proud of our technical support. We never leave behind any of our customers. We do quite a lot. We support our clients even out of turbomachinery field, for example, in numerical mathematics, physics, or software engineering. And also the real tutorials are included in TCFD, so the user has no doubts about the best practice settings. The real machines are included and preset, so basically it's very easy to start using Turbo-Machinery CFD. There are many other benefits of Turbo-Machinery CFD. I'm going to finish with my last point, that Turbo-Machinery CFD is developed in a way to support the users in their value-added activities. So Turbo-Machinery CFD is automated, and the user, it's the user who decides how deep to dive into CFD problems, or whether just to use it as a tool. So that's the way we go, and that's the way we develop Turbo-Machinery CFD. Okay, I think it's time for the second live example. So it's now simulation part of the webinar. It's TCFD. Radek Maca. So Radek, are you ready for your part of the presentation?
Yes, I am, Bosch. I am. So you can give me the presentation, please. Okay. So yes. So I think you can see my screen. So hello again to everybody, and hello to Oliver, which I'm ashamed that I forget to say hi to Oliver. So hi to Oliver, and what is the topic of my part? So in this part of this webinar, I'm going to show you the general workflow of our TCFD software. So thanks to the Oliver, which has designed and export the centrifugal fan geometry. So using this export, my task is very easy now, because everything is preset to import this data to TCFD and run the simulation by a few clicks. So I will directly go for that. So I will find the export from CFturbo, which I have placed here. So as Oliver has already noticed or pointed, that the export from CFturbo generates the configuration file, TCFD file we called, which basically contains all necessary keywords which basically preset the CFD simulation, including what is the input geometry, what are the boundaries, what are the simulation points, type of machine to simulate, and so on. So everything is preset. And here in STL directory, there are each part of the designed geometry. So I can open it just by clicking on this STL. For example, I can open all these STLs to just see and visualize the geometry. Okay, so now you can see everything is loaded. I can group it together and to show you the principles how the input should look like. So if I colored by these colors, for example, so the import is split into so-called components, which really follows the design part in CFturbo. So basically the stators and rotors should be split into separate components, as it is here. So the rotor part and the stator part must be separate because for a general safety workflow we have to define a special treatment between the rotation part and the stator part, and this is done automatically with CFturbo. So basically the geometry is nicely split into separate files and separate geometry parts, and then we can nicely assign each boundary type and we can design and set the meshing process with respect to each part of the geometry, which also are automatically exported from CFturbo. So this is the input data we need for successful run. Again, the STL geometries and the configuration file. So now to start working with TCFD, I need just one click on this configuration file, and automatically the TCFD graphical user interface appears automatically. So as you can notice, the graphical user interface is implemented into the ParaView, which is an open source multi-platform data analysis and visualization application, which contains a huge amount of filters, which combination gives you almost unlimited post-processing power. So we connected the setup part of the CFD simulation together with this post-processing application, which gives you really unlimited options how to process your geometry and how to evaluate it. Nevertheless, a lot of work is done automatically with TCFD. So I load it, I can click on apply, and automatically our design is loaded into the TCFD. It is automatically split into defined components. So basically it follows the workflow which Oliver showed us. So the rotor part, the white one, and the red part is the volute part. So here is the pipeline browser. Basically at the beginning we have this TCFD file which contains the settings and the components visualization to see really the geometry. And here are several menus in which we can set or we can modify whole CFD workflow and CFD setup part. So at this moment, I will just go for the simulation. Basically, here's the most important part using the CFturbo export. So I need to just define how many processors I have available on my computer. Now I'm using, let's say, 3 or 4 years old laptop, so I have just 2 processors. So I will set 2 processors because there is no sense to use higher amount of processor which I have not at the moment for use. So just 2, and every other is set up. Maybe I will come back later to describe briefly these menus. So at the end of my setup part, I can click on the settings, and now we are coming to the last phase, which is the simulation run. So I just click on settings. Here the TCFD manager icon is enabled, so I can click on apply. And this is the so-called TCFD manager. And basically here by few clicks, we run the simulation. So first of all, I should set the directory name. For example, my webinar simulation. So it's up to user. I click on apply to commit this name. Afterwards, I write the case. It means it writes into this directory all necessary configuration files, boundary conditions, geometry definition for a successful run. So now this is saving, perfect. And now I can run all automatically. So I will do that because everything is preset. So this run all basically contains 3 steps. First one is the meshing process, which is now performing. You can see component 1, which is the rotor, is now meshing. Then after the mesh is done, then the calculation is run automatically. And at the end, the report is generated. So we will have all the meshing parameters and at one place in HTML format, as we will see in few minutes. And this is the end. Yeah. So that is all. Now the simulation is running, and I should just wait a few minutes to get the results. So to fill this gap, I will go back to the setting part to show you what is possible to change, what is possible to set. So in the setting part, what we have here is several menus. So there are, let's say, chronologically sorted. So you can go step by step. So first one contains in which configuration file your setup will be saved and which machine type you would like to simulate. So this software provides several machine types, from compressors up to water turbines, let's say. inside the simulation menu, we can set the number of processors. There is no limitation. You can use thousands of processors if you have HPC's hardware, and so on. You can switch between first and second order schemes. Of course, you can set the physics, so air for radial fan, water for water turbines. Here in components, here we set basically the computational domain using each STL. So we basically assign, for example, impeller hub is assigned as a hub, and here are some levels of refinement at this boundary. So all these STLs are assigned as some physical type connected to CFD. We can add layers, of course. Here there are background mesh size, so these numbers defines the maximum size of the cell in your computational mesh, and other parameters improving the meshing efficiency. And of course, which is a nice tool, is this topology graph, so how your geometry is completed. Where is the inlet, where is the outlet, where is the intersection or interface between different components. And what I can notice, or what can I point, that on each interface between rotor and stator, you have to apply the method of communication between these parts. First one is mixing plane approach, which defines some averaging mixing planes on which each variable is transferred. So now we have 5 mixing planes. If we define 0, so for 0 the so-called freezing rotor is applied, or AMI approach in the language of OpenFOAM, or yeah. Okay, so I will let it to 5. So in this way, each component is set up. Afterwards, of course, we have to define the computational points. So we call it speed lines. So you can design, or you can simulate several regimes of the fan with the different rotation speeds and with different operation points. So usually to get nice efficiency graph, so usually define several points among your designing operation point. For each point, you have to define inlet and outlet boundary condition, which describing your operation point, usually different volumetric flow rates or different pressure drops, and so on. Then of course, you have to place initial conditions, so some reasonable guess for pressure, velocity, and other variables. Inside the simulation controls, there are some advanced parameters, such as relaxation of the solver, some boundings of the solver, which can improve the robustness of the simulation process. The post-processing, inside the post-processing, you can, for example, set your favorite units, for example, pascals or atmospheres, torrs, and other for pressure. You can set the efficiency probe, which is really useful. So implicitly, the efficiency or pressure drops are evaluated at the inlet and at the outlet of your geometry, but you can also impose this efficiency just on the rotor to see really the efficiency of the rotor only. Blade-to-blade views, we will see afterwards that it automatically generates some meridional views and meridional average variables, as well as the blade-to-blade views, as we will see in a few minutes. And some other meshing options, advanced, so it is really advanced option regarding the SnappyX mesh, which is used for automatical meshing. And of course, the scripting gives you, again, unlimited unlimited power to tailor the TCFD to your needs. So that is all. So we can go back to TCFD Manager to see the state of the simulation. So we can see that after the meshing, all these columns are colored in green, which shows you that everything was meshed properly, and now the simulation is run. So we can see that now the point 1 is simulating. It simulates now more than 100 iterations. There are 30 minutes left to get the results for the first point. So always you are informed about the simulation. Anytime during the simulation, you can click on the light report and it will generate the actual state of the simulation. So this is done. And at the end of the simulation, it automatically generates so-called full report, which I can show you because I have run the simulation before the webinar. So I have it here. So this was my working directory, and in each working directory there is a report, so we can anytime access this report. And now I will just give you a brief overview of this report. So at the beginning there is nice header which shows you the shape of your geometry. It contains basic simulation statistics such as flow rate during the simulation, residuals during the simulation, the mesh size, the clock time, how long does it take to get the results, how many processors I have used for this simulation, special variable for fans such as fan characteristic for each computed point and nicely depicted in the figure. For example, you can click anytime on the figure to enlarge it and see the details. Of course, the efficiency map. So we can see that the best efficiency point is somewhere around the flow rate 11, and it reaches over 85%. And also, all these values are tabulated or listed in this table. And of course, you can follow the convergence process of efficiency to see if the efficiency is stable during the computation or not. Of course, the torque, again, you can anytime click on the figure, total pressure difference, total pressure ratio, total pressure per interfaces. So these are graphs for each simulating point, and you can, for example, see what is happening at the wheel inlet, what is happening at the wheel outlet, or what is happening at really the outlet from from the domain. The same is for the total temperature, or this total temperature difference. And for example, this is total temperature per interfaces. So again, you can list and go through all the interfaces. And at the end, for example, I can show you the automatically evaluated images. So blade-to-blade view with the streamlines. So we can efficiently and nicely do the visualization analysis of your machine, for which point or where some recirculation occurs, so which part can be optimized, and other nice. You can really do some statements from these results. Besides this, you can, as I said, that Barreview gives you unlimited power, so you can visualize your own images using our filters, Turbo Unwrap and Meridional Average. So this is just original wheel with total pressure contours. You can do the same for unwrapped wheel. You can also do your own meridional average with, for example, arrows which points or which shows you the flow field. at the meridional plane and turbo unwrap with LIC filter with with the streamlined visualization. Well, I see my clock that my time is almost up. So just to conclude, the TCFD is very smart and efficient CFD tool. It can be smoothly connected with CFturbo software and really is ready for the automatization and optimization process. Okay, so this is all from my side because I'm short on time. So thank you, and let's go back to Luboš. So Luboš, can I give you the presentation back?
Yes, of course.
Great.
So thank you. So I guess it's me again, right? So can you see my screen?
Not yet.
Okay, so I'll do the. Okay.
All right.
Okay, now it's me again. So yeah, thank you, Radek, for the simulation part of the webinar, and now it's the final part of the webinar. It's the Q&A. So I would like to ask all the participants to put their questions, and we will answer some of them right here in this webinar live, and if there will be some more questions remaining, we will answer them for sure by the email. So we keep the record, so don't worry. Okay, you can put the questions. Yeah. So let's take a look what we have. Okay, it's so can I? Yes. Okay. Not too many questions. So yeah. So this is mainly the technical question. So we have a question, perhaps on Oliver, which is, what is the difference in design of blades of a pump, turbine, and compressor?
Yes, there are, of course, Euler equation of turbo machinery applies to all of these machines. But apart from this, there are a lot of really big differences. So, for instance, the empirical databases of correlations is quite different. Also, the fluids that are conveyed with, for instance, gas turbines or compressors have to be considered as being compressible, and also in those kind of machines you might run into shocks and stuff like that. On the other hand, with pumps, for instance, there might be the problem of cavitation. So there are a lot of big differences which are phenomena that come from the fluid to be transported, but also in general from the set of empirical correlations.
Okay, thank you, Oliver. The next question is also to Oliver, I guess, which is from Mike. Is an airfoil profile blade available in the CFturbo? I'll give you, Oliver, back the presentation to you.
Okay.
Right.
All right. Yes, I can. In general, I can say yes. It is especially useful for actual fan design, because if it comes to actual fan design, one can apply airfoil design theory. But it can be also applied in the centrifugal or radial fan design. So, for instance, I can go back to the meridional view and can go to the blade profiles design step, and here I could I just make it it's identical from hub to shroud. Here I can just click on with the right mouse button on the thickness line and have access to a built-in profile manager, and from that profile manager I can choose from different profiles that are that will be shipped with CFturbo, but this profile manager can be also extended by the user. And especially for this design step, one can use the thickness distribution that is connected to those special airfoils. But for the, as I already said, for the actual fan design, the complete profile can be used.
Okay. Well, I think I can't see any more questions. So yes, so I think it's, yeah, perhaps it's time to conclude. So I'll take back the presentation. So yeah, I think it's time to finish. So feel free to contact us. I'm sure you know very well how to do that. The questions about CFturbo are to be sent to CFturbo. The questions about Turbo Machinery CFD are to be sent to CFD support, and we will gladly support you in your projects. It's our job and also a pleasure. So yeah, so time to conclude. So Oliver, anything to say?
Yes, I like to thank you for your time, and well, next year I think we're going to have another of other presentations. So, and I would be happy if you would listen to us again. Thank you.
Okay, thank you. Radek, would you say hello?
Oh, yes, thank you very much for your attention. And if you have any technical or any other question, we gladly answer you later on via email or via Skype or yeah. So anytime you can send us anything. So thank you, and see you or hear you sometimes in future. Bye.
Okay, so it seems to be it from us. So thank you for your attention, and we would like, yeah. So yeah, bye bye. Yeah, bye bye.